On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds into its flight, claiming the lives of all 7 astronauts aboard. The Presidential Commission on the Space Shuttle Challenger accident, known as the Rogers Report, identified the failure of rubber O-rings sealing the joints in one of the boosters as the cause of the accident. The specific failure was the destruction of the seals that are intended to prevent hot gases from leaking through the joint during the propellant burn of the rocket motor. 1. The external tank was destroyed, leading to the breakup of the orbiter. Tragically, the possibility of an O-ring failure had been known for some time but was not properly communicated. Although the original cause of the disaster was a faulty design, the immediate cause, defective O-rings costing just a couple of dollars, lent its name to Michael Kremer's idea of an O-ring production function. Point 2. In contrast to the classical view of output as a deterministic function of some inputs, production is viewed as consisting of a wide range of independent subsystems all prone to failure and succeeding only if none of the subsystems fail. The earliest example of a possible application in defense was the suggestion to interpret an aircraft carrier's flight deck operations as an O-ring production function. Point 3. That is, unless everything falls into place, catastrophic failure may result, as the USS Forrestal accident on July 29, 1967 sadly demonstrated. An example of an O-ring-like sequence, though not in name, is provided in the book Naval Operations Analysis. It states that for a submarine to succeed in destroying an enemy submarine, it would first have to detect it, then identify it as the correct target, work out a firing solution, launch the torpedo at least and political opportunity structures, multiplied, as opposed to summed, to reflect that all components are necessary to have a chance of winning in unconventional warfare. Point 5. The F-35, a state-of-the-art O-ring production function generally considered the most advanced fighter plane in existence, the F-35 not only displays extreme maneuverability and lethality but is a platform incorporating all the subsystems needed to conduct a strike against surface and aerial enemy targets alike. Still, it is an O-ring production function. Sticking with the OODA paradigm, a pilot unable to observe or orient would be unable to decide, let alone act. Thus, if any of an F-35's subsystems are incapacitated, either kinetically, by means of a cyber attack, or just by jamming, the whole platform is basically rendered useless. The mathematics behind the O-ring production function elucidates the dilemma. The scenario assumes there are 4 tasks or subsystems needed to successfully complete a mission, such as observe, orient, decide, and act. The probabilities for these tasks to be successfully met are denoted by P1, P2, P3, and P4, respectively. The probability of mission success, assuming stochastic independence, is given by P1. P2. P3. P4, and the probability of mission failure by 1 P1. P2. P3. P4. 2. Give a numerical example. Even if every subsystem has a 90% chance of doing exactly what it is supposed to do, the mission success probability is 0.9, 4 equals 0.6561. That is, the mission will fail in more than 1 out of 3 cases. If the subsystem success rate is increased to 95%, the probability of failure would go down to 0.95, 4 equals 0.1855, but the mission would still fail in almost 1 in every 5 cases. One would be mistaken, though, in assuming that increasing a subsystem's reliability is an easy way to alleviate the problem. Prima facie increasing all subsystems' reliabilities by 5 percentage points to increase the overall success probability by roughly 24%, from 0.6561 to 0.8145, looks a great idea. The cost of increasing any subsystem's reliability is exponential. It would cost less to increase its success probability from say 70 to 80% than increasing it from 80 to 90%, and the additional cost becomes ever more prohibitive the closer one gets to 100%. In terms of the O-ring production function theory and denoting the cost functions by C pi, this reads as C greater than 0 and C greater than 0, to illustrate the effect by using the simplest functional form for an O-ring compatible cost function. C pi equals 1 pi. If a subsystem's reliability were to be raised from 70 to 80%, the cost would rise by 50%. Raising reliability from 70 to 90% would triple the cost. Finally, it should be superfluous to point out that a success probability equal to 1 is impossible to achieve. Just as man is not perfect, there are no technologies available that never fail. From US not only air superiority to anti-access area denial throughout history and up to and including World War II, warfare has largely been a numbers game. At the beginning of the Pacific War, the Zero was the most advanced fighter plane. Japan didn't have enough of them, though. In contrast to their American counterparts, Japanese pilots had combat experience, but again, there were too few. The German Tiger was considered the best tank of its time, vastly superior to say the American Sherman. Luckily for the Allies, though, there were many more Shermans around than Tigers. All of this is in line with tactical warfare models. Radley Fisk in 1905 and Frederick Lanchester in 1916 suggested that, in naval combat and aerial combat respectively, doubling a force's quantity should be more important than doubling its quality. Incidentally, unbeknown to Lanchester, a paper written by G. Hugh Chase in 1902, when he was a lieutenant at the Naval War College, was a forerunner in describing naval warfare. The mathematics were the same, but Chase, in contrast to Lanchester and Fisk, had even taken staying power such as defensive characteristics into account. Using his model, Chase pointed out the advantages of the tactics of isolating enemy forces. This recommendation led immediately to the paper being classified. It was not declassified until 1972.6. From the end of World War II and through the Cold War decades, however, the picture changed as the US attained an ever-expanding gap in weapon technology advances over its peer rivals, Russia and China. The simple reason was economics. Just as a command economy could not compete with a free market economy, neither could its defense industrial base. Russian numerical superiority did not help. The higher kill ratio of US weapon systems would have sufficed to halt Russian forces. Russian submarines could be tracked wherever they went, but not vice versa, and Russian commanders knew this. Precision bombing during the Vietnam War saw the advent of the one bomb, one target capability. US air superiority achieved its heyday during Operation Desert Storm. US stealth fighter bombers could enter Iraqi airspaceable, and as General David Depchler noted in 2001, the Gulf War began with more targets in one day's attack plan than the total number of targets hit by the entire 8th Air Force in all of 1942 and 1943, more separate target air attacks in 24 hours than ever before in the history of warfare. 7. The picture changed with 9/11 and the ensuing wars in Afghanistan and Iraq for 3 reasons. First, top-of-the-line air combat platforms were no longer considered necessary for counterinsurgency operations. Second, The cost of fighting two wars at the same time pushed back other expenditures, leading to a reduction in the numbers of F-22s and F-35s. Third, airspace was implicitly assumed to continue being uncontested. However, having had ample opportunities to study the American way of war over the decades, U.S. forces had reigned supreme. Developments and military expenditure chose to take an altogether different path. Rather than trying to play catch-up, they changed the game by embarking on doctrinal responses and strategies that would render U.S. forces' superiority useless. The two countries would simply bar access to disputed areas, such as the Baltic Sea or the South China Sea respectively, and/or deny the ability to operate in those areas, i.e., A2, AD. In particular, by area denial, U.S. operations in the respective area would be impeded or slowed down at best, effectively preventing U.S. forces from pursuing the fundamental principle of tactical warfare, which is, as the U.S. Navy puts it, fire effectively first. 8. Any attempt to enter the contested battlespace would be met by a both fierce and relatively cheap resistance. The cost of a Chinese DF-26 carrier killer anti-ship missile comes at a fraction of any of its intended targets. It would make U.S. losses